Now that we've tested a single proportion to an assumed or historical proportion, we'll extend hypothesis testing to testing two proportions that are collected from two groups. Our essential questions are: what are the three sets of null and alternative hypotheses for testing proportions? What are steps 1 through 6 for testing two proportions? Or more specifically, how do they change compared to testing one proportion? How do you evaluate the sample size assumption for two proportions? What do you do if you don't meet it? And is there a rule that we can follow? And what is our universal decision rule for making a statistical decision? So far, we've learned how to state a question in the form of two hypotheses with a null and an alternative. We've talked about assessing your data. We've talked about answering the question using a statistic and an associated p-value. And we've learned how to calculate confidence intervals. It turns out we can do all of this when we're testing two proportions as well. So if you recall back to the null and alternative hypotheses for a single proportion versus a null proportion, we either had equal to, not equal to, less than or equal to versus greater than, or greater than or equal to versus less than. And we used a critical value originally to look at z statistics, but you can also set an alpha level and use p-values. And that's much simpler because you don't have to continue looking up z-values in tables. You can simply get the p-value out of your software and continue to use the universal decision rule based on alpha. For our p-values, we're going to choose the null hypothesis when we have a large p-value, if it's bigger than alpha. Or we're going to choose the alternative hypothesis when we have a small p-value that is less than alpha. So now we only need to set the significance level of alpha. So this is, to review again, our decision rule, and our alpha is usually set at 0.05, though it can be really any number that you want to assure that you only make what is called that type 1 error in the one direction. Remember, the type 1 error is assuming the null is true. What is the likelihood I'm going to choose the alternative anyway? And we usually set that at a small percentage or 0.05. When we have one proportion, remember we compared p naught versus p hat, or the null versus the observed, and we calculated a confidence interval for that observed proportion. We assumed p naught was known. That's usually not the case in scientific research. What usually happens is you're going to collect two new groups. Your new intervention or your new treatment or your expected new something happening versus your standard or control group, it's often called. So with two proportions, let's look at the ECMO study. Remember, it was designed to determine if an ECMO-based protocol would increase survival without severe disability by 6 months after randomization compared with conventional ventilation. So we're calling that survival. We have two groups here. They actually treated people, one set of group with ECMO and one set of the other group with conventional ventilation, or the conventional method. We'll abbreviate it CM. So if we go into our steps for hypothesis testing, we can review them. Phase 1, state the question, has 3 steps. Phase 2, decide how to answer the question, has 3 steps. Phase 3, answer the question, also has 3 steps. Notice that we make all of our choices about how we're going to make our decision before we calculate the test statistic in phase 3. And phase 4 is a single step, and that's documenting our entire understanding of the question, the data, the results, and our interpretation of those results with text, tables, and figures. For the ECMO results, how do these steps get applied in the case of comparing two proportions? If we look at table 3 in the paper, it will help us evaluate and describe the data. They have shown death or severe disability at 6 months as a no, which actually means that the patients survived. So they've sort of formed this in the way of a double negative. It's not something that I would generally recommend. You should try to formulate your groups or your hypotheses in terms of positive results, because it's more easily understood than saying they didn't die proportion. It's much more conventionally accepted to talk about survival. So think about how you would present things, but this is from the table, 3 in the paper. We can actually put things in terms of a contingency table, which actually shows both the yes and the no. So you can see here I've reformulated this to be in terms of survival. This is simply the counts. This would leave your reader to do the math themselves, and they may make a mistake. So when you're looking at a tabular display called a contingency table or a crosstab or cross-tabulation or two-way classification or a 2x2 table, you may want to actually add more than just what we've observed. So if you remember, we had 57 out of 90 ECMO that survived and 41 out of 87 conventional positive pressure ventilation or conventional method patients that survived, or 98 out of 177 total survived if we ignore the groups. But again, this is a lot of counts, it's a lot of numbers, and you still haven't given the proportions to your reader. So you may want to actually use a histogram to do that. This is simply a very straightforward bar chart. I did this one in Graph Builder and Jump, but you could create it in Excel or any other graphing software that you have. It simply shows the proportions that have survived. We don't always need to show the proportion that didn't survive. Obviously, it would be 100 minus 63.3. When we compare proportions, we're either going to compare the proportion surviving in each group or the proportion that didn't survive in each group. We are not comparing the proportion that survived with ECMO to the proportion that did not survive with CM, and we're not comparing 63.3 to 50%. This isn't a test of, was it half and half? This is a test of, is that 63.3 similar to that 47.1% in the CM group? A histogram is helpful. You could also put the proportions in a table. Notice that the columns total to 1 and the rows total to 1. So that out of those surviving, 63% were in the ECMO group, 47% survived in the CM group. So that's your column proportions. But you could do it the other way. So you really have to sort of think about the best way to present it for your readers. Again, proportions maybe not necessarily the best. You might want to do percentages. So asking what proportions of everyone received ECMO, of those receiving CM who survived or did not survive. Remember, we're only comparing the proportion that did survive in the two groups or the proportion that didn't survive in the two groups. We're not comparing proportion survived to the proportion that didn't survive, nor are we testing for equality of the proportion equaling 50%. What we want to know is the proportion of those surviving the same in the ECMO group compared to the CM group? Probably the best table is one that actually looks at the status with the percent and the N. People tend to understand percentages more than proportions, and so this puts it in terms of something that they can really understand. We can also show the total ECMO group and the total CM group and the proportions in each of those. We could show the percent survival overall. That's our 98 out of 177. Or we could show the 90 out of 177. This is a very clear table. It doesn't leave it up to the reader to do any math. And then when you're explaining your results, it's easy to reference by the column, yes or no, and the ECMO or CM. Now we need to review the assumptions. It's the same assumptions as we had before: representativeness, independence, and sample size. Are the subjects in each group representative of the sum population of interest? We have already covered this. We know it's random sample and they were randomly assigned to the two groups, so we're okay on representativeness. Independence. Does the response of one subject depend on the response of another? If that's the case, if the answer is yes, say you have people from the same household, or you have family members, there might be some relationship between your rows or your cases, then they're not independent and you need to stop with this 10 steps of hypothesis testing and utilize a different type of test for paired results. We'll talk about that in the future. If they are independent, then the response does not depend on another response and we can continue. In this case, barring other information, they appear to be independent. We also need to assess sufficient size. Remember, in the single population case, we actually looked at expected for 5 responders and non-responders, or 5 survivors and non-survivors. We'll do the same in the 2x2 situation. We need to calculate the expected, not the observed, the expected number of subjects under the null hypothesis of equal proportions. And we need to have an expected larger than 5 in all 4 of our table cells. So let's first state our hypotheses and then we'll come back and look at our sufficient size. So in this case, we're actually going to look at the proportion of ECMO equaling the proportion of CM versus our alternative of ECMO not equal to CM. We can reformulate our 3 sets of hypotheses, proportion 1 versus proportion 2, in this way. It's very similar to the null proportion P0, but now we've changed it from P to P and P0 to P1 and P2. Remember, if our null is true, then our 2 groups are said to be homogeneous or uniform. The 2 proportions are the same. If they are the same, then we should consider a single proportion overall. We can think of our null hypothesis now as ECMO equals conventional equals some sort of true average survival rate. The best way to calculate this is to take our total number of survivors in each group and divide it by the total N. That's our 98 out of 177 in the ECMO example. This is called P bar, or the average. And in our case, it's equal to 0.5537, or 55.4% of people survived. Now we can revisit the sample size estimation. If our true proportion is the same for both groups, then we can use P bar to look at sufficient size. How many people do we expect to see in each of the 4 cells in our 2x2 table? You can see the notes for the details of the calculations. We'll actually see in the jump video how to get it out of jump. It's much faster and easier than having to do the math yourself. What you need to know is this rule. If more than 20% of your cells have expected counts less than 5, then we have to use Fisher's exact test. The sample size assumption is violated in the case of 20% of cells having expected less than 5, and we cannot proceed with a large sample or Z statistic. In a 2x2 table, we only have 4 cells. So any one cell expected is actually 25% of the cells having expected less than 5, and we violated the sample size assumption. In our case, if you take a look at the notes, or when we visit it in JUMP, you'll see we're okay for sample size. We can proceed with the remainder of the steps. Ask yourself, after representativeness and independence, is the assumption for our statistical test met? The answer is yes. Then we can trust the sample proportion will be normally distributed. If we can trust that, then the sample proportion is normally distributed, then we can calculate a p-value. If we can calculate a p-value, then we can make a decision with understandable risk. That brings us to phase 2, decide how to answer our question. So we know we have a null hypothesis of ECMO equaling CM, but you can actually just ask if the difference between them is 0. This makes our statistical test quite easy. So when you look at one proportion, we had 3 possibilities. In our case, we're looking at 2 proportions, and we're asking, is it the same proportion or are they different proportions? If you remember our generic test statistic from p hat versus p naught in the one sample case, this is what z looked like. We can modify that for P2 and P1. Notice here we have P2 minus P1, so P2 would be our ECMO group, and P1 would be our conventional group. We're going to compare that to 0. So just like we had P hat minus P naught, in this case, we're creating a difference between the P hats and comparing it to a P naught or an assumed difference of 0. We're going to use the standard error under the null hypothesis, and that's actually just represented by the P bar and the N1 in ECMO and the N2 in conventional medicine. How could random variation affect the statistic we've chosen? Remember, if the null is true, then z will be 0. If our proportions are not different, z will be 0. If these are really the same, then this will be 0 minus 0, and our z statistic will be 0. If they're only slightly different, then we still expect to see very small z values. We expect to see some very small differences. Extreme values of z, so if there's a large difference in our proportion, that will result in a large z statistic. That will favor the alternative. Then we can state our decision rule using the statistic. And again, we're going back to our universal decision rule. Choosing the null hypothesis if our p-value is bigger than alpha. Choosing the alternative hypothesis is if our p-value is smaller than alpha. And again, this is usually 0.05. Large p means we pick the null hypothesis. Small p means we pick the alternative hypothesis. Steps 1 through 6 take very little adjustment when we are testing 2 proportions versus when we tested 1 proportion. We still have 3 sets of hypotheses, though equality is the most commonly used one. It's usually equal to, not equal to. We have to evaluate all 4 cells in a 2x2 table for the sample size assumption. All 4 have to have expected greater than 5, or we need to use what's called a Fisher's exact test. And our universal decision rule has actually remained unchanged. Since we're relying on a large sample test and an underlying distribution, all we have to do is select our alpha, usually 0.05, and we'll choose our alternative if our p-value is smaller than alpha. Up next, we'll actually look at the remainder of the steps and determine how to actually carry out the proportion testing, either using an Excel spreadsheet or using statistical software.